Welcome to Study Loop.
Okay, folks, so in this video we're going to be talking about this problem. We have a wire 50 centimeters long that carries a current in the positive direction of an x-axis through a constant B field of this magnitude. And what we're going to be looking for is we're going to be looking for the magnetic force in unit vector notation. So we're looking for the B force on the wire in the unit vector notation. Okay, so let me just draw this problem out for you so you have a better visual idea of what's going on. So let's say this is the x-axis, this is the y-axis, this is the z-axis, and what you have here is you have a current running in this direction. What you also have here is you have a B field that lies in the YZ plane because it's something times J hat plus something times K hat. So due to my limited, artistic capabilities, I'm not going to be able to draw it out perfectly, but I just want you to see approximately what's going on, right? So this is your B field, and it's a constant. It doesn't depend on where you are. It's a constant. And if you do your cross product between I and B, you will find that the result of the cross product is going to be perpendicular to I and also perpendicular to B. So it's going to point somewhere in this direction, right? But anyway, that's basically the idea. How are we going to find the magnetic force? Well, we're going to start off with this following formula. If we have a charge dq and it's moving with velocity v and it's moving in a constant magnetic field, then it's going to feel a force given by this formula, right? This right here is the Lorentz force, except it doesn't have an electric field. So usually the Lorentz force is given by, force equals Q V Q V cross B plus E, right? But since we don't have an electric field here, we're just going to be considering this part of the Lorentz force. But because we have a wire, right? We have a wire. We don't just have, one little charge. We have a wire. So what we're going to do is we're going to do a little bit of an integral and sum over all of the charges that are moving in this 50 centimeter long of a wire. Okay, so this is dq. What we're gonna do now is we're gonna take this formula, rewrite it a little bit, and and that's gonna make our notations a lot cleaner. So we have v is just the distance over time, right? Cross b, and what we can do is move this dt under dq to make that an I, right? And dl cross b. But because dl is a vector, we can move that vector sign to I, right? Because dl and I are in the same direction. I cross b dl. This is what we're end up with. We're end up with I cross b times dl integral. Okay, and we're integrating over, what are we integrating over? We're integrating over the total length of the wire, the wire. And because I and B are both constant along the wire, in other words, it doesn't depend on where you are on the wire, we can pull this whole thing out of the integral because it's a constant from the perspective of the integral. So we have I cross B, which is a constant, multiplied by the integral dl, right? And what is the integral of dl? That is obviously just the total length, which we know to be 50 centimeters, multiplied by I cross b. Okay, so this is the total force on the wire all we're left to do now, all that's needed to do now, is to find the current as a vector and the B field as a vector, do a cross product, and we have our answer. Okay, so what is I, what is B? This is what we need to know. Well, I, because we know the current is flowing in the positive x direction, so we can write I as this. It is 0.5 and then 0, 0 in the y and z direction. What is B? Well, B is, it does not have an x component, so I'm going to put 0 here. It does have a y component, which is 3 mt, and it also has a z component, which is 10 mt. Okay, so this is our current vector. This is our B field vector. What we're going to do now is do a little bit of a cross product. So we have x hat, y hat, z hat, 0.5, 0, 0, 0, 3 mt, 10 mt. You do the determinant, that's going to give you I cross B, right? So, because we're running out of time here, I'm not going to do the determinant. Yeah. So after you're done watching the video, I highly encourage you to do this determinant out yourself on paper, and that is going to give you the answer. So actually, after you're done doing the determinant, you're going to have to multiply that by the total length of the wire, which we know to be 50 centimeters. After you're done doing everything, you will find that the force is negative. It doesn't have an x component. It has a y component, which is negative 2.5 mn, and it also has a z component, which is 0.75 mn. This right here is the answer to this problem. Okay? Thank you very much. See you in the next video.